All right, so now at long last, we finally get to be introduced properly to the Black-Scholes model. Now, I mentioned this the other day. The Black-Scholes model was kind of a revolution in finance, and in particular in the area of derivatives pricing models. Although the authors of the Black-Scholes model apparently did not fully appreciate at the time how important this would turn out to be. In fact, one of them wrote a paper afterwards and did explain, what they expected to happen, and they were pretty surprised themselves when they discovered that this was so revolutionary. And so they were able to tackle a problem that had been eluding mathematicians and financial analysts for many decades. And in order to do it, though, they needed to borrow from a brand relatively new field of mathematics called stochastic calculus, which had only really been introduced maybe 15 years earlier by a Japanese mathematician named Ito. And so Ito eventually won, I think it's called the Fields Medal. It's whatever they have in math, it's equivalent to the Nobel Prize in economics. There's no Nobel Prize in math that you probably know. What prize in math is equivalent to the Nobel Prize in economics? Um, huh. I thought, yeah, the Fields Medal. That sounds right. The Fields Medal is often considered the mathematical equivalent of the Nobel Prize. Oh, it's only given out every 4 years. I didn't know that. Oh my God. So anyway, so Ito won the Fields Medal for his discovery of this area called stochastic calculus, and without which the Black-Scholes model completely depends on it. If the field hadn't been invented yet, then the Black-Scholes model would never have happened. So sometimes in science, you'll notice how one discovery depends on another one and another one and another one. So anyway, so the Black-Scholes model is only able, though, interestingly enough, to do one thing, and that is to price European call options. And even then, only on non-dividend paying stocks. In other words, the original Black-Scholes model is very specialized. If you have an option on a stock that does not provide any dividends during the lifetime of the option, then you can use the Black-Scholes model to price it. For anything else, you need to do something a little different. Although later on, Black and Scholes and Merton in particular were able to extend the model to price many other types of options. But the one thing that the model cannot do is price American options. Okay, we'll discuss that as we go along. So anyway, the paper finally appeared in print in 1973. It was published by the Journal of Political Economy, which doesn't sound like the most logical choice for a paper like this. The paper was rejected by 8 of the most prestigious journals in the field. I'm sure they are still sorry about it. And eventually it landed at the Journal of Political Economy. And so the original paper is a model that explains all the parts of this option pricing model that they introduced. It also explains a lot of the assumptions that they made. And we'll see in a few minutes that they did make quite a few assumptions in order to make this model tractable. And some of those assumptions are more realistic than others. So we'll see what some of these are. And then we'll see how to actually implement the Black-Scholes model. Now here, for the first time, what we're going to do is I'll show you how to do this in Excel, and then we're going to see if we can turn this into VBA code, because as you'll see, the VBA code is very similar in this case to the Excel commands. And so this is a case where, even though it's a fairly complicated model, writing VBA code will not be too terribly difficult once we understand what happens in Excel. So I think I mentioned the other day that, in economics, the Nobel Prize tends to be seen as sort of a lifetime achievement award. They don't often give it out after something important like this happens. It took until 1997 before the Nobel Committee got around to this model. Yeah, I guess there was a big backlog. And also, like I said in the beginning, there was some skepticism about how valuable this model would prove to be. But by 1997, it was clear that this was a revolutionary model. So they did award the prize to Scholes and Merton. Black didn't get it because he'd already died, sadly enough, but he would have it if he still was alive. There's others. If you look at the list of Nobel Prize winners in economics, often they're quite old. It's almost like they're somehow there's something about being in economics that increases their longevity. You'd be surprised how old some of those winners were, but these guys weren't that old. They were, I mean, by the time even when they got their prizes, I think they were probably still in their 60s, and so this proved to be a huge deal. And also, the thing about the Nobel Prizes is that in economics, at least, they tend to rotate between different subspecialties. Like one year it might be international finance, the next year it might be public policy, then the next year it might be econometrics, which is the statistics of economics, and then they get around eventually to the financial papers. And it took a while before financial papers were given Nobel Prizes in economics. There was a time when finance was perceived to be a very different discipline than economics, but now it's pretty clear that they're both really part of the same area. Anyway, here's some of the assumptions we need to look out for. For one thing, the returns to the asset underlying the option, in this case, it would be a stock, are normally distributed. Okay, now we're gonna, by the way, I wrote up a separate document here, which is on Blackboard. And what I did was I wanted to sit down and write out in more detail what's going on behind the scenes with the Black-Scholes model. So if you recall, if you've had any statistical background, you'll recall that the normal distribution is the one that looks like a bell-shaped curve. Okay. Let's see if I can draw another graph of this thing real fast. So we have some variable, which is assumed to be normally distributed. And this curve is meant to represent the probability that that variable takes a value within a given range. So for example, let's say that we're assuming that let's say take something simple. Suppose that we assume that the rainfall in New York State is normally distributed with a mean of 30 inches per year. And let's say a standard deviation of 5 inches per year. So what they're basically saying is that it follows this curve. The curve itself can tell us the probability of a variable attaining a specific value. So let's let X represent the rainfall in New York during a given year. So the mean is 30. The mean is here. And that's often, you'll see this often designated with the Greek letter mu. And in this case, that would be 30. Okay, so that's at the center of this distribution. Now, if you notice, it continues on. It actually continues on forever until positive net infinity on the upside and negative infinity on the downside. So basically, this line you're seeing there is the real number line. The curve represents probabilities for particular values of X. So we're also told that the standard deviation is 5. It's designated with the Greek letter sigma. And basically, this gives us a sense of how spread out the values of X are likely to be from the mean. So for example, here 35 inches would be thought of as a single standard deviation above the mean, and 25 would be one standard deviation below the mean. So we can use the normal distribution to calculate the probability of, let's say, X being between 25 and 35. Now, I just happen to have this one memorized. It's 3413. Okay. We'll see we've calculated that in a few minutes with Excel. But that means there's a 34.13% chance that the rainfall this coming year will be somewhere between 25 and 35 inches. The reason why we can figure this out is because of the assumption that the rainfall is normally distributed. So no matter what the mean and standard deviation are, the possibility of being in this range within one standard deviation of the mean is always 0.3413 or 34.13%. And then we could do the same thing if we wanted to try the probability that we are within, let's say, two standard deviations of the mean. And so in principle, we can calculate any probability that we want for the rainfall in the coming year by using the normal distribution. So, by the way, if you notice, it has an interesting property. What's going on below the mean and above the mean should be identical to each other. So the distribution said to be symmetric about the mean, meaning that the two sides are mirror images of each other. That's a huge deal. That really makes it a lot easier to calculate probabilities for the normal distribution. This property of symmetry, so what's going on below the mean is the same as what's going on above the mean. Now, because what's going on under the curve represents probabilities, that implies that the entire area under this curve between negative and positive infinity is going to add up to 1. Because 1 represents 100%. So X has to be somewhere in that interval. So therefore, the probability of being in that interval is 1. Okay, so all the other values are taken from that. So in other words, 0.3413 means 34.13% of the total. Okay, the entire area is 1, which is true, by the way, for all probability distributions. It's not just the normal. And so we are treating probabilities are calculated as areas under this curve. Okay, so we're saying that probabilities correspond to areas under this curve. All right, so in other words, it's defined that way intentionally to make sure that areas and probabilities mean the same thing. Okay, so this is our normal distribution. By the way, we can have any mean and standard deviation we want. It'll still have a very similar shape. This thing is called a bell-shaped curve because of the way it looks. But no matter what the mean and standard deviation are, the basic shapes will be very similar to each other. Now, let me just quickly show you, though, what happens when we do change the means and the standard deviations. For example, I'm going to draw two different normal distributions here. And the first one has a mean of, let's say, 0. The second one is 10. But they both have the same standard deviation. Okay. Now, the drawing is not perfect. They're supposed to have the exact same shape. You can see I didn't get it quite right, but the idea here is that these are two normal distributions, and they have the same standard deviation. So they are equally spread out from the mean, but their location is different because the first one has a mean of 0, and the second one is 10. So if we have two normal distributions, and by the way, there's an infinite number of possible normal distributions, because there's an infinite number of possible combinations of the mean and standard deviation, which by the way are not restricted to being integers. So there's literally an infinite number of possible normal distributions, and you'll know by looking at them what their mean is by where they're located. On the other hand, the standard deviation determines their shape. Okay, so the standard deviation determines the shape or how spread out the distribution is from the mean. Okay, so here I'm going to draw two new normal distributions, except this time they'll have the same mean, but two different standard deviations. So this one, let's assume it has a mean of 0 and a standard deviation of 1. And this one has the same mean of 0, but its standard deviation is, let's say, 10. So you can tell by looking at them, the second one, the one with the standard deviation of 10 is much more spread out than the one with the standard deviation of 1. But they're still bell-shaped curves, if you notice. It's just that the stretching, it's more stretched out or spread out with a higher standard deviation. So to summarize, the mean determines the location of the normal distribution on the real number line, while the standard deviation determines the spread of the distribution from the mean. Now, if we're modeling not rainfall, for rates of return to assets, the standard deviation can be thought of as a measure of risk. Because it captures the uncertainty over the returns to an asset. Okay, so if we're looking at specifically a rate of return, let's say we have two stocks. And let's say, now here, we're going to have both a different mean and standard deviation. So tell you what, let's make this a different color. Well, all right. I should have started it further to the left, but you get the idea here. So you notice how it's not quite so tall, it's more spread out. And so the mean, let's say, is 10, and the standard deviation is 20. And let's just say we'll call this stock B, and this is stock A. And these are not prices, by the way, these are rates of return that we're looking at here. So the important thing here is that at a glance, you can see stock A has a lower average rate of return, but it is less risky than stock B because it has a lower standard deviation. So there's more returns close to the center. It's not so spread out, but in exchange for that, you also have a lower average rate of return. And this is what you normally expect to see in the market. Normally, stocks or any other assets for that matter with the highest rates of return also have the highest level of risk Otherwise, you know what would end up happening. If both of these stocks had different returns but the same standard deviation, everyone would buy the one with the higher rate of return and sell the other one, and then the prices would adjust until the stock with the greater risk has the higher rate of return. Okay. You're not going to see two stocks with the same return and different risks, or at least not for very long. So this is the kind of thing you expect to see. So if you're a conservative investor, you're more likely to buy stock A. And if you're a little bit more aggressive, you might buy stock B. Of course, you can buy both, but and we'll see what that would do later on. But right now, what we're trying to think about is their statistical properties as measured by the mean and the standard deviation of the returns. So the returns are assumed to be normal, and this is what that implies. Okay. Now, once we know the mean and standard deviation, that we can draw them, and we can calculate probabilities. Let's say, for example, I want to know that if I buy stock B, what's the probability that it'll get a return more than 15% next year? Now I can figure it out very quickly and easily with the normal distribution. So it turns out the normal distribution is really one of the more useful statistical distributions. And in fact, we see it used all the time in many different disciplines. It's very convenient and often conforms to what we see in the real world. Not that there's not others that are good too, but this one is the one you're most likely to run into, in my opinion, especially in this chapter when Black and Scholes themselves assumed normality for the returns to the assets that we are writing options on. All right, actually, I might as well save this and I'll send you, put it on Blackboard so you'll have a copy of this too. Let's see. Okay. By the way, if you own one of these wonderful TI-84 calculators or something similar to that, all of this is in here. You can calculate any probabilities you want on this calculator if you have, if you know what you're doing, of course. But luckily, we don't really need to do that because Excel also has the capability of calculating normal probabilities. And we're going to see how that works. And then we'll see how VBA does the same thing. This is, by the way, one of those cases where you might find conflicts between VBA functions and Excel functions. They may occur in both and yet have different spellings. All right, so that's the normal distribution. By the way, why is this assumption being made? Because it's largely true, but also if you don't assume normality, you have to pick something else. And that something else is likely to be a lot more complicated than the normal distribution. And at some point, you have to ask yourself if it's worth the extra complexity. Let's say that our actual stock returns they're normal up to a point, but not completely normal. Do you really want to toss the normal assumption and replace it with something much more complicated in exchange for increasing the accuracy a little bit? The chances are, in this case, no. The normal distribution is going on behind the scenes of many types of statistical analysis. And so using something else is a very, let's say, complex process. You always have to ask yourself, like, sure, if I use something else, it might be slightly more accurate, but is it really worth it? So the fact that we're still seeing the Black-Scholes model being used with the assumption of normality, what is it now? 50, I guess they had their anniversary last year of this paper. It's 51 years now. The fact that people are still using it 51 years later means that they agree that we may as well continue to stick with this assumption, even though it's not technically completely correct. Now, it turns out that there's two important ways in which this assumption is violated in practice. And that'll have an effect on the accuracy. What I've done here is I've shown you the black curve is the normal distribution. The red one is the typical returns to a stock. And so if you notice, the assumption is off in a couple of important ways. Number one, if you notice, the red curve is slightly to the left of the black curve, which means that the actual returns that we see in practice tend to have slightly lower average returns than is suggested by the normal distribution. And then also the shape is slightly different. It's not perfectly symmetrical. As a matter of fact, the way it's drawn, there's an imbalance, or there should be, between losses and gains in favor of the losses. So in other words, instead of having an even balance between losses and gains, or at least getting returns above and below the mean, in practice, we tend to see more returns below the mean than above. Okay. So that situation is described as the curve is said to be negatively skewed. So, and then if you notice the red curve is slightly taller than the black curve, which means there's more returns below the mean than you would get with the normal. Now, just in case, what I've done is I've added here a little bit more discussion about for what are called moments. We've already seen the mean or expected value, as it's sometimes called, and the standard deviation. Actually, let me mention every probability distribution has four key measures which describe its properties. They're known as moments. The first one is, you notice how it's called here the expected value. The expected value and the mean are the same thing. These are the formulas you could use to calculate, depending on which distribution you have, the expected value or mean. Okay, so in fact, what I probably should have done is thrown in here the mu, just to remind us that these are the same thing. Uh-oh. I think I'm having an issue with my marker here. Yeah, all of a sudden it's not working. You know, all right, well, here's what we're gonna do. I'm gonna unplug this one and replace it. I have another one. It's so funny how this is my fairly expensive tablet, and it keeps giving me a lot of grief. I have a cheaper one over here, which I don't use unless I have to, and it always works. The expensive one is kind of a piece of crap, to be perfectly honest. So I'm going to just make a little switch here. Okay. Okay, there's the Greek letter mu again to remind you this is a mean of a distribution. By the way, you need to see these words here, discrete and continuous. Let me just quickly mention what that's all about. in case you don't have this background, with a probability distribution, or a probability distribution can fall into one of two basic categories. It's not impossible for there to be other categories, but these are the most common ones. A probability distribution can usually falls into one of two categories. One of them is called discrete, and this means the number of possible values is finite. Number two, continuous. Number of possible values is infinite. So with our rainfall example of fall, the number of inches of rain can be a fraction. So because of that, the number of possible rainfalls over the coming year is infinite. Okay, so that means, so let's mention this here. The rainfall next year would have a fractional value so that the number of possible rainfalls next year is infinite. Therefore, since X represents rainfall next year, the probability distribution of X is continuous. Now, what would be a counterexample is, what if I said instead, suppose that X represents instead the number of days that the Yankees are rained out next year, or actually, since the season's still going on, I guess I could call it this year. X must be an integer. In fact, it must be a non-negative integer. So that X is a discrete, or X is discrete. Or I should say, the probability distribution of X is discrete. Okay? It can, it could be 1, 7, 8, whatever, but it can't be 3.7, for example. So the normal distribution is a continuous probability distribution. All right. And so that's why we can use it for things like rates of return, which themselves can be have an infinite number of possibilities. Okay. Now, let's get back to now here is again this extra document that I wrote to help us understand the Black-Scholes assumptions. And while we're at it, maybe I should add a title to it. Just so you don't come back to this later on and say, what is this all about? Okay, so that's why I've got it listed twice, but these are the formulas you would use. Now, if you notice with a continuous distribution, we're going to use calculus. F of X, by the way, in the continuous case is the formula that we're using of this black curve, the normal curve. This is actually simply a graph of a function, which I believe shows up in the slides. It's some function which we'll call f of x, which assigns probabilities to every possible value of x. So that f of x is sometimes called the actually, ooh, what happened here? This is one of the things I have to watch out for. If I try to move the headings around, it can cause a mess with the drawings. Oh boy. I hope that's the only. Oh, uh, all right, I'm going to quickly fix this. Oh, I see what happened. There's three skewness cases. Okay. All right. It looks like it's okay now. Otherwise, you won't be able to read it if I don't, if I don't fix it. Um, Boy, this is just unbelievable. Well, I guess we'll have to fix it as we go along. All right. Oh, Jesus. Yeah, this is really frustrating as can be. All right. Yeah, let's just carry on. We'll fix it as we go along. There's no point in sitting here all day. All right. What the hell's going on? All right, so we may not get to all this stuff today anyway. So we'll keep going. Anyway, so where we left off was we're looking at these moments. Okay, so the mean or expected value is done in the following way. So as I started to say, um, this f of x, I'll put it on this document. F of x represents the probability density function for the normal distribution. This is the equation or function that is used to calculate normal probabilities. So this PDF, as it's called, is what characterizes a probability distribution. If for a now this is for a continuous distribution. The terminology is slightly different for the discrete distributions. P of x represents the probability mass function, as it's called, or PMF, or a discrete probability distribution. Again, this is the function. is used to compute probabilities. Okay, so when you see that in the formula, that f of x is the formula that the normal curve represents. So you're integrating it over whatever interval is relevant. The mean for the entire distribution, you're integrating over negative to positive infinity. But when you're calculating probabilities, you're integrating over only the interval that you're interested in. Now, we're not going to do any of that here. I mean, that's what the normal function in Excel does for us and in VBA. It's behind the scenes, it's doing an integral of that f of x function over the interval that we're interested in. So that's the first moment of any probability distribution. The second is called the variance. Now, the variance is closely related to the standard deviation. In fact, the variance is nothing but the square of the standard deviation. Okay, but we think of the variance itself as the second moment. The standard deviation is the square root of the variance. And this is what we're using as our measure of risk with rates of return. So let me just mention here on this document, the variance of the distribution is the second central moment, it's called. The standard deviation is the square root of the variance. So here's the good question. Why do we bother? Why don't we just use the variance in the first place? The variance has one inconvenient property. It is measured in square units. In other words, for example, if Apple stock returns are normally distributed and the variance is 0.09, this is interpreted as 0.09% squared, which is a very difficult thing to get your mind around. So because there is no interpretation for a squared percentage, the standard deviation is used instead. Standard deviation is then the square root of 0.09, which is 0.30, which in turn represents 30%. Okay, so that means the standard deviation of the stock is 30%, or the risk, 30%. And when we say 30%, by the way, we mean usually per year, although it could be other time frames. So there's usually a time component when we're dealing with rates of return to stocks or other assets. And that's true of the mean as well. If it says the mean is 10%, that usually means 10% per year. So one more thing I wanted to mention here, I think we discussed this the other day, the standard deviation of the returns to a stock or any asset is known as volatility of the asset's returns. And as we saw, the VIX index represents the volatilities of the stocks on the Standard & Poor's 500. Actually, let me just double check that. I have to make sure it's not the 100. It is 500. Okay, I just want to make sure. Okay. There's so many other indexes besides the one we hear about all the time. Like there's a Standard & Poor's 100, for example. There's all kinds of indexes, but this is one of the more important ones. And so I showed it to you, I think, the other day. It looks like an EKG, for God's sake, like somebody's getting a heart reading or something. It goes up and down and up and down and up and down to reflect activity in the market. Anyway, now those are the first two moments: the mean or expected value, the variance. But there's two more that are harder to visualize what they refer to. And so we're going to introduce those now because this is important because it helps us understand the ways in which the Black-Scholes model assumption of normality is incorrect. If you notice, it doesn't make any assumptions about the mean or the standard deviation. It just assumes normality. But here's the issue. The third measure or moment is called skewness. Now, the way the skewness is calculated, and on purpose, 0 means that the distribution is symmetrical about the mean. The normal distribution is assumed to be or is symmetrical about the mean. If the skewness value is positive, that means there's an imbalance in the right tail. The right tail is bigger than it should be. If the skewness is negative, then the left tail is bigger than it should be. So if you go back to our graph here, you'll see that, well, maybe I haven't drawn it as well as I should have, but skewed to the left in the sense that there's more area in the left tail than there should be compared to the normal distribution. And yes, these are called tails, by the way. These extreme ends of the distribution are called tails. So here we have a circle around the right tail, indicating positive skewness. Here we have a circle around the left tail, indicating negative skewness. Negative skewness in the case of returns means that there's an imbalance in favor of returns that are below the mean rather than above the mean. So this is one of the problems with our Black-Scholes assumptions. This is what's actually happening in practice. We're assuming skewness is 0. And then finally, we have this one, which is really kind of hard to wrap your mind around, called kurtosis. What is this all about? Well, it basically is a way of measuring how fat the tails are compared to the normal distribution. So the kurtosis is defined in such a way that 3 represents the normal distribution. Now, greater than 3, we say the distribution has fat tails, which is what you're seeing here, which means there's more area in the tails and not so much in the middle. And this is what we see typically with rates of return. They have fat tails, meaning that extreme outcomes are more likely than what you would get with the normal distribution. And that works in both ways, by the way. We have more extremely poor returns and more extremely strong returns compared to what you would get with the normal curve. Now, less than 3, you don't normally run into this in the financial markets. Skinny tails means it's the other way around, meaning that you're less likely to get extreme outcomes than you would with the normal. Okay. In practice, this is what you see. If your distribution of returns is not does not have a kurtosis of 3, chances are we have fat tails. Now, by the way, if you notice with the skewness is defined in such a way that 0 means symmetrical, negative means negative skewness, positive means positive skewness. So 3 is not a terribly intuitively useful number. So there also exists a related measure called axis kurtosis, which is regular kurtosis minus 3. And the advantage of doing this is that 0 means you have the same tails as the normal distribution. Positive means you have your fat tails. And negative means you have skinny tails. All right. And it's just a lot of people find it easier to think about it in those terms. Also, Excel's kurtosis function, as we'll see when we get there, is not really a true kurtosis. It is actually excess kurtosis, although they don't really tell you that. The way they calculate it, the number they're giving you actually is this excess kurtosis. Not a smart move, in my opinion, but there it is. Okay. Now, one thing I just noticed, this thing, this is not, does not have any page numbers. Let's fix that right now. There you go. This is one of the stupidest things I've ever seen. Microsoft Word does not assume you want page numbers. I don't understand what they're thinking. But anyway, where what else are we assuming? So the volatility, meaning the standard deviation of the returns to our underlying asset, is assumed to be the same throughout the lifetime of the option. This is probably the worst assumption of all of them because the volatilities can change very quickly. So we're assuming constant, like let's say it's 22% today, we're assuming that until the option matures, it'll stay at 22%. But in practice, volatilities can change sometimes very quickly due to market forces. Now, the risk-free rate of interest, meaning the yield on treasury bills of the same maturity as the option, are assumed to stay constant during the life of the option. This is not a terrible assumption. Interest rates don't really change that quickly. So those are there's others, but these are the most important assumptions. So we're going to see as we go along how that can affect the results. Now, as I think I mentioned the other day, even though the original Black-Scholes model was only meant to price equity options or stock options where the stock doesn't pay any dividends, Merton in particular came along with a series of papers in which he showed that actually we can relax these assumptions and use it to price options on just about any asset we can think of, as long as they're European options. So you got now suddenly, oh, commodities and currencies and interest rates and stock indices and futures contracts. The sky's the limit now. So he really opened the doors for a lot more types of options. And sure enough, in the marketplace, a lot of these options started being introduced in the late 70s after these papers came out. And also after it became clear that there's a need for these options to hedge risk. Okay. In particular, if you ever had an economics course, you know that after just around, actually, just as World War II was winding down, the Western European nations and the United States set up what's called the Bretton Woods Agreement, where the currencies were tied together at a specific rate, and they were all in turn tied, the dollar rather, was tied to the price of gold. And the purpose of doing this was to eliminate foreign exchange risk, to encourage trade between these countries and rebuild their economies. So while this was going on, there was no real need to hedge foreign exchange risk because there really wasn't any. These exchange rates were fixed and known to everybody, so they couldn't change. Once the system was abandoned in the early 70s, suddenly there's all this foreign exchange risk in the market. So Wall Street came along with currency options to help manage that risk. And then in the late 70s, interest rates started skyrocketing because of inflation. And suddenly it became clear that market participants needed protection against interest rate risk. And so here we are. Suddenly Wall Street introduces interest rate options. And so a lot of these options came about just because there was some specific problem that needed to be addressed. And so sure, they were profitable for the Wall Street companies, but the ones that were chosen were often in response to some specific development in the markets. So now, and you can see suddenly this opens up the floodgates. Now you can have options on just about anything you could imagine. And so finally, with all that being said, we're going to take our first peek at the actual Black-Scholes formula. Now, it looks surprisingly simple, although we still have to define D1 and D2. What's not simple is the way it was derived. That's the part that got them the Nobel Prize. But for actually pricing options, this is all you need. Now, by the way, these ends refer to the normal distribution, as we'll see in a bit. So let's take a look at this thing. What do we need to know? Well, first of all, let's copy this onto the next slide. Oh, let me make that just a little bigger. All right. So the C is the call price. With the actually, S is the stock price, or if this is not a stock option, S could be thought of as the spot price of the asset. Like if this is gold, for example, a gold option, then S would be the gold price. Okay. X is the strike price. R is the risk-free rate of interest, which means the yield on a treasury bill that has the same maturity as this option. And T itself is the maturity of the option in years. Now this tells me that we're calculating probabilities from the normal distribution. So these are both probabilities. Whoops. This whole expression is oh boy, it won't. There we go. That's a probability and that's a probability based on this function D1 and D2. So what are they all about? This is the definition of D1. Now, if you notice here for the first time, we've introduced the volatility value, sigma, which means in turn simply the standard deviation of the rates of return of this asset S. Ln, of course, is our old friend natural log. The reason why it's there is because we're using continuously compounded rates of return. This is something we have to discuss. Here we go. I think, yes, what I'd like to do is right here at the bottom of page 4, have a brief discussion about what do we mean by continuously compounded rates of return. So, wow. See, the problem is if I put it in here, I'm going to goof up the rest of this thing. Not necessarily. Oh, yes, necessarily, I guess. Let me see what I can do. If I get it comparable to where it was, it shouldn't goof up the graphs too much. Yeah, here we go. Yeah, see, unfortunately, this part is a little bit mangled. We will fix this, but not today, obviously, because it's already, yeah, that's what I was afraid of. All right, I'll tell you what, here's what we're going to do. I'm going to stop here. What I'd like to do is take a little bit of a detour and introduce this concept of continuously compounded rates of return, explain what they are, and then carry on from here. Okay, so we'll stop here. I'll post what I have so far, but just be aware that on this document, some of the graphs got a little bit mangled. And we'll fix this next time. Maybe I can fix it right now. Hold on a second. I'm not sure what this is doing here. Yeah, this is gonna be a bit of a mess. Maybe not. Actually, it looks pretty good now. I don't know what all those blank spaces, but anyway, so my idea here is to let's see. All right, we're gonna leave off right here with our discussion. Yes, what does it mean to be continuously compounded? And then we can get back into what we were doing. So, all right, let me save this. So I'm going to post it on Blackboard with it. I'm going to actually put a new date on it so you can tell it's from today. And then plus the notes we were just working on. Also, we didn't get to it yet, but there's a spreadsheet where we're going to do our examples in Excel, and then we're going to see how to translate them into VBA. Okay. But for now, sadly, we have to stop. And so I'll see you all again next time.